Okay, so today we're going to be talking about density. So density is equal to mass per unit volume. And usually it is represented by the Greek letter rho. So row your boat. All right, and the units on density are, of course, mass per volume. So, I mean, it can be anything, but since we're going to be dealing with SI units, generally we're going to be seeing here grams per cubic centimeter, grams per milliliter, and these are actually the same thing. So grams per cubic centimeter, grams per milliliter, exactly the same. We can also see kilograms per cubic meter or grams per liter. So, it depends. All these things, we can easily see. Notice on the top here, all these are units of mass. On the bottom here, all of these are units of volume. So, those will be seen very commonly. Next up, the density here has a dependence on temperature, pressure, and the phase. So if you're dealing with a liquid, a solid, or a gas, the densities are going to be very different. So you have to make sure exactly what phase you're dealing with. Now, as for the dependence on the temperature and pressure, well, the pressure is kind of easy to understand. If you're taking a substance, so let's say I'm taking my pen here, and if I'm squeezing it really, really hard, well, in that case, if I'm squeezing really hard, my volume is going to go down, even though my mass stays the same. So if I squeeze really hard, the volume decreases. That means my density is going to increase, right? So that means for this, high pressure is going to yield high density. Okay. And then as for the temperature, well, if we're dealing with gases, it's quite easy to understand because in that case, the gases are going to be moving faster if you heat them up. They're going to start expanding, and your density is going to decrease. If you're dealing with liquids or solids, generally that's what happens as well, but there are some big important exceptions like with water. So for the temperature, here we can say that usually hotter is less dense. So that's usually what happens, but again, underline the usually because for water, there is a exception. And there are a couple other substances, but water is by far the most famous. Here we have a plot of the density of water on the x-axis in grams per cubic centimeter versus the temperature in degrees Celsius on the x-axis. Now, solid water or ice starts out on the left, and notice that the density of the solid ice is around 0.91 to 0.93 grams per cubic centimeter. Once it reaches the melting point, which is at 0 degrees Celsius, there is a large discontinuity and the density jumps up to nearly 1.00 grams per cubic centimeter. It then slowly increases and reaches a maximum at 4 degrees Celsius, and as is shown in the inset, and slowly decreases after that as it goes towards the boiling point of water at 100 degrees Celsius. But at no point is the density of the liquid lower than the ice, and this is why ice floats on the water, because the ice is always less dense than the liquid. Then after the water boils, the density of the steam decreases dramatically to nearly 1,000th of the value of water. If you're doing high precision work, then you would need to know the density to 4 to 5 decimal places. However, as a good first approximation, if you know that the density of liquid water is approximately 1.0 grams per cubic centimeter, then you have a good starting point for the calculations. And by the way, these large discontinuities at the melting and boiling points, these are the marks of a phase change. So for any material, if you see a large change in density which occurs at one temperature, then a phase change has occurred. Now, one property of having more dense materials is that the more dense things will actually sink. So if I have here some container and I put in a bunch of liquids here, and let's say these liquids are immiscible, meaning that they don't dissolve in one another. So it's like oil and water. They don't dissolve, but we can order them via their density. All right. So if I have here liquid 1, liquid 2, liquid 3, liquid 4, we can know what the order of these densities are because I know that here the density. So this is going to have density of 1, that's going to have density 2, that's going to have density 3, that's going to be density 4. So the most dense object is going to be down here, and the least dense thing is going to be up on the top. right? So this is going to be, my density of 1 is going to be greater than the density of 2, and this is going to be greater than the density of 3, and this is going to be greater than the density of 4, you know, and so on. So this means that you have less dense things always floating on top of there, and that's of course why wood floats, because wood is less dense than water. And also, if you think about it, you know, when you have a glass of water, the air is on top, the air is less dense than the water, and that's why the water is in the middle there. Interestingly enough, if you happen to have two liquids which have basically the same density, but they are immiscible with one another, then you can kind of get them to sort of dissolve. And in that kind of a case, you can actually get something like this. So you can actually have here like L1, and then you would have kind of like L2 in there. So this is what would happen if you have like L1 and L2 are basically the same, but they don't actually interact. So you can actually get kind of like a blob of the stuff floating in the middle, because, you know, there's the density of this is not going to be 100% uniform. It might be just a little bit more dense here on the bottom than on the top. So you might actually get a blob kind of floating around, you know, actually in the liquid like that. And that you can actually make some of these liquids if you try for that. And you can get that in a lava lamp, where the red lava is actually going between being more dense and less dense than the liquid it's in. And that's why it goes up and down, and in the middle, you know, it has the same density as the liquid that it's in there. Here's an interesting little fact. Can a more dense thing float? And the answer to that is yes, assuming that you do it correctly. So first of all, we can use surface tension. And the way you can do that is on the top of the water here. So if we look at, you know, our liquid, and let's assume this is water. Well, there's an interface. So this is going to be air up here, and then we have the liquid. And between this interface, there's this surface tension. That's the whole reason, you know, water feels wet. You know, it's stickiness. It sticks to the sides of everything. So this is that little bit of this adhesion, the bonding of these molecules here. Between, you know, the air and the water interface, there's this little bit of surface tension, and if you apply something very, very carefully, you can actually make something which is denser than the liquid actually float on top. So that's one possibility. And then the second possibility is to make the average density of your solid less than that of the liquid. And this works in what is known as a boat. A boat. Okay? And the reason, of course, this works is, you know, here is my liquid level here. So there's your boat in the water. And I draw my little boat, goes below there, comes back up. And basically, even though, you know, the boat is made of steel, which is much more dense than the water surrounding it, you have this entire empty void in the middle, and that makes the boat on average less dense than the water, so it will float. Of course, if you overload the boat, such as if you spring a leak and water starts rushing in, well, then the boat will definitely sink. Okay, so this is definitely you know, the way that you can actually make a boat and make things float. So the surface tension, this is actually used a lot by bugs. If you ever see like little bugs walking across the water. Okay, so what we have here is just a regular old glass of water, and we're just going to put a paper clip on top just to demonstrate, you know, how the surface tension can actually hold this thing up. And there you go. Now the paper clip, which is made of steel or aluminum, is actually much more dense than the water, but is actually floating there. And actually you can see in the video there are some distortions right around the paper clip in the light, and that's because you know, the surface of the water is actually being distorted slightly. And I can bob this up and down, you know, as long as I don't do it too hard, but, you know, causing little ripples in there, and you know, it doesn't sink. I mean, if I really go up and down a lot, then of course it will fall down. But I can make this, and notice I'm just putting this in there, no problem. But now in this little dish I have some soapy water, so I'll just touch a little bit of soap in there. And if I touch this to this stuff, gives it a second, see, it falls down. And that's because once I added the soap, and then the soap slowly spread over the surface, it reduced the surface tension of the water, and it was not enough to actually hold up the paperclip anymore, and it just fell right through. And of course, you know, using boats, and, you know, they can do this with ducks as well. They will float quite nicely in the water. So here in the book, we actually have a nice little table giving some typical densities for solids, liquids, and gases. First of all, notice the units here on my solids and liquids are both grams per cubic centimeter. or grams per milliliter. These are the same. And then down here we have the density of the gases as grams per liter. These are fairly typical densities. Of ice, like I was saying earlier, is about 0.917 grams per cubic milliliter per milliliter. Rubber is more dense than that. Magnesium and aluminum, they're fairly comparable there. And aluminum, of course, aluminum cans, that's why they use it a lot in materials, because it is, they say it's light, but they really mean it's less dense. Iron is fairly heavy, of course, so it's very dense. Lead is the perennial dense material, it's fairly cheap. And then gold is very dense, and you may have heard the story about how Archimedes figured out that whether or not you had gold or silver was by looking at the difference in the density between these two materials. And so gold is very, very dense. Now, actually, the densest material is listed over here on the previous page, is actually osmium. Okay, so osmium is an element. It's actually very dense. It's 22.5 grams per cubic centimeter. Iridium is also very close. It's like 22.4, so it's just a tad below of osmium. But really, this is going to be like the highest value that we actually see for a normal material. So when you're dealing with calculating densities for a test or any problems like that, if you start getting values that are over 23 grams per cubic centimeter, right there is a big hint that you may have goofed up somewhere, because normal materials that we have here on Earth do not have densities that high. So that's really a big clue that you may have goofed. So this is like a good number. Density shouldn't be higher than, like 22.5 grams per cubic centimeter. So just keep that number in mind. All right, and then as for the rest of these, so here we have some liquids. We have ethyl ether, ethyl alcohol, ethanol. And this is about 0.789. Water is actually 1, so some nasty typo here in the book. Chloroform is 1.48, and mercury, of course, is the liquid metal, which is very, very useful. Unfortunately, it's very toxic, so it's not used quite that often anymore. But it has a very, very high density here, 13.6 times that of water. So it's very, very dense, and if you've ever, used it or picked it up, it's quite remarkable how heavy, a small amount of mercury actually can be. And then here we have the gases, hydrogen, helium, ammonia, air, oxygen. So here, they're all around, maybe around a gram or so per liter. The basic thing, if we start looking at, some general trends of solids, liquids, and gases. So this is if we're just dealing with the same material. So here, the solid density is going to be approximately the same as the liquid. And these are both going to be much greater than that of the gas. Okay, so solids and liquids, same order of magnitude about there. So these are going to be on the order of 1 to 10 grams per cubic centimeter, thereabouts. Meanwhile, the gases are going to be a thousandth of a gram per cubic centimeter, or 1 gram per liter. So it's going to be much, much less than this. And as we saw, from those units there, gases are going to be approximately 1,000 times less dense than the liquids and solids. And that's exactly what we were seeing here for these. That's why these are in grams per cubic centimeter over here, and then these are grams per liter, because there's that factor of 1,000 difference between them. And one little important caveat just to mention here, for this little thing, this is at atmospheric pressure. So atmospheric pressure is basically what you're feeling right now, and room temperature. Okay, because it's very easy to take a gas, and gases are very compressible, and squeeze it or heat it to very high temperatures, and then this thing will be completely wrong. But if we're just talking about gases at atmospheric pressure and room temperature, this 1,000 times difference generally holds pretty well. So it's a good kind of rule of thumb just to keep in mind. All right, so let's do a little example here. And so again, we remember that the density is equal to the mass per volume. And let's say that you want to make a solid gold statue life size of yourself. How much is your solid gold statue actually going to weigh? So of course, if we want to do this, we need to know exactly how much gold we need to order. So first of all, we're going to need to know a couple of things. First of all, the density of gold. And that was just from the book, as we saw, that was 19.3 grams per cubic centimeter. we need to know and I want to put this in a separate column here. We're also going to need here, so the mass over volume, so that we need to know the density of a person. And that's 1.02 grams per cubic centimeter. Okay, the mass of your person is going to be 70 kilograms, and we're going to need to know what the volume is. And then we're going to use that volume over here, which is going to be the same thing. And then the mass, we're just going to figure out what that is. So right over here, all this data here is for, the human. And then this data over here is for the gold. So, it's very easy to measure the mass. You can figure out the density of the person just by looking at the tissues. You can kind of look at that. So that's around 1.02. So we're just going to figure out, what the volume of this person is, and then say, we're going to make, a solid gold statue with, life size. So it's going to have that same volume, and we're going to figure out what that mass is actually going to be. We're just going to solve here. 70 kilograms divided by my volume is going to be equal to 1.02 grams per cubic centimeter. Now, obviously, I have here 70 kilograms. This is 1.02 grams. So we're just going to have to rewrite this as 70 times 10 to the third grams per volume is equal to 1.02 grams per cubic centimeter. And then I just go my 70 times 10 to the third divided by 1.02. So my volume is going to work out to be 68.6 times 10 to the third cubic centimeters. Okay, so that's this value right here, and I'll just write that in. So that's 68.6 times 10 to the third cubic centimeters, which is the same, 68.6 times 10 to the third cubic centimeters. And now that I know my volume over here, I can very easily just solve for my mass. So just doing this one down here, my mass is going to be equal to my density times my volume. So this is going to be equal to 19.3 grams per cubic centimeter. And then my volume, 68.6 times 10 to the third cubic centimeters. My cubic centimeters cancel out, I'm left with grams. So that's going to work out to be 1.324 times 10 to the sixth grams of gold. Right. So obviously quite a bit. Not just for fun, let's figure out, how much your solid gold statue will actually cost you. Right, so we can just easily convert this we can just convert this to ounces, because that's usually the way gold is sold, at least in the US. So we have here 1 ounce is 34 grams. And that's going to work out to be 4.67 times 10 to the fourth ounces of gold. Okay, and we can figure out how many pounds that is, divided by 16. But we want to know the price, and the approximate price is about $1,200 per ounce of gold. So if you multiply these two numbers out, we're going to wind up here with 56 times 10 to the sixth dollars, or basically 56 million. If you want to build a solid gold statue of yourself, life size, it's going to cost you about $56 million there. All right, now as for something a little more tangible, let's figure out, what is the density of the Earth? So density of the Earth. Well, that's just going to be the mass of the Earth over the volume of the Earth. All right, so the mass of the Earth is 5.97 times 10 to the 24th kilograms. And then the radius of the Earth is equal to 6,378 kilometers. And we want this units to be in here in grams per cubic centimeter, so we can, compare it to our other values we were seeing. All right, now, first of all, we have here the radius. We need to get the volume. Of course, the Earth, to a first approximation, is a sphere. So we know that the volume here is equal to 4/3 pi r cubed. So that's just going to be 4/3 pi times my 6,378 kilometers cubed. So this is going to work out to be 1.0868 times 10 to the 12th cubic kilometers. Of course, we want this in cubic centimeters, so we have to convert this, and just as a Nice little reminder on how we do that. 8 times 10 to the 12 cubic kilometers. And then let's see, we got here 10 to the third meters per kilometer. Cube that. And then 1 centimeter is 10 to the minus 2 meters. Cube that. And just to remind ourselves, that's 3 times 3, so that's going to basically be a 10 to the 9 over here. And then that's 10 to the minus 2 cubed, so that's 10 to the minus 6. 1 over that, so that's going to be 10 to the plus 6. So 9 and 6, that's going to be 15, plus 12, that's going to give us 27. Okay, so that's going to be 1.0868 times 10 to the 27th cubic centimeters. And then, of course, this one up here, we need that in grams, so that's going to be 10 to the third grams per kilogram. That's going to give us 5.97 times 10 to the 27th grams. All right, and actually just notice 10 to the 27th cubic centimeters, 10 to the 27th grams. So actually that's kind of good because these two numbers basically cancel each other out. So actually that's kind of nice, and we're just going to be left with the 5.97 over that. So we can very easily just figure out what my density is here. So the density is going to be equal to 5.97 times 10 to the 27th grams over my 1.0868 times 10 to the 27th cubic centimeters. And that's going to work out to be 5.49 grams per cubic centimeter. So, this value makes sense because, it is less than the osmium, which was, like we said, about 23 grams per cubic centimeter. So, even though there are obviously some areas on Earth which are much denser than others, on the average, the Earth is about 5.5 grams per cubic centimeter, and that's actually fairly typical for the terrestrial planets. If you go to the gas giants, they're going to be much less than that because they are mostly gas. But for the Earth and Venus, Mars, Mercury, the Moon, their values are on this order. Maybe a little bit less, maybe a little bit more, depending on how much iron and stuff they have. But this is a fairly typical value.